Right. This is going to be section 3.3 and 3.4. So let's get started. We already did a little bit of section 3.3, but let's look at this problem. We've got a car driving up an inclined plane, and it's going to drive a certain distance, and we're going to want to know, let's see, a car drives up a steep 10-degree slope at a constant speed of 15 meters per second. After 10 seconds, how much height has the car gained? Okay, this is a great problem. I think it's going to be really helpful for the homework. And this is perfect. Okay, so first things first, let's read the problem carefully because I think a lot of problems with doing these types of things come because maybe you don't read the problem carefully, and so you're not aware of what it's really asking you for or what's happening. Okay, so the first thing is, well, as usual, of course, draw a picture. Okay, just so that way we have everything absolutely clear. Okay, let's switch to. There we go. Okay, so it says that the car is driving up an inclined plane. Okay, and so Charmander, he's gonna run up this plane. Okay, and it says that, see, what is Charmander's velocity? Okay, he's going 15 meters per second up the plane. Okay, so 15 meters per second. So that's going up the plane. Okay, and this is at a 10-degree angle here. Okay, so Charmander's booking it. All right. That's about 30 miles per hour. Right. So man, he is really cruising. Okay. Ash is in trouble and he is trying to get there to help Ash. Okay. And we want to know what is the height that Charmander travels up the slope during this time. So the best way to do this, I think, is to find the component of our velocity in the y direction right here. And 15 is the hypotenuse of our triangle, so we're going to find our velocity here. This will be Vy. The opposite side here, this is, yeah, Vy, and then Vx is this way. Okay, so we're going to find his component of velocity in the y direction, and then we're just going to see how far he traveled. Okay, because it tells us in the problem that the time Charmander traveled is 10 seconds. Okay, so when I read the problem, I think about what are the things that I know and how can I use that to get to the answer? I know his velocity going up the ramp here. And I know this time, so the time's probably going to be important. So first things first, let's find his y velocity. Okay, or you could do this another way. We could find the distance here as well too. But let's try it this way. We're going to find his y velocity, and so that's going to equal v times sine of theta. Okay, and that's going to tell me how what is the height that he's gaining as a function of time. Okay, so I'll put my numbers in here. This is sine of and 10. Okay, so I'm going to put this in 15 meters per second times sine of, that's going to be 10. Okay, so let's go put that in MATLAB. All right, so we got 15 meters per second times sine of 10 degrees. And okay, so that tells us now his Salamander's y velocity. Salamander's y velocity is, his y velocity is, of course, 2.6 meters per second. All right. So, um, now we know the time as well. And so we're going to use one of our equations of motion now. There's no acceleration because he's traveling at a constant velocity. And so I'm going to write y equals vy times t. Okay? And so then it's going to be 2.6 meters per second. I'm just going to plug in my y velocity that I found there, times 10 seconds. Okay, so that's going to be, it looks like it's going to be 10 times 2.6 or 26 meters. And my seconds cancel out here. And that is going to be the change in my height. All right, so what did I do? Well, I found the component of y velocity here. And then I used this equation of motion here to calculate what was the distance that he changed in that amount of time. That's how I did the problem, okay? And that's how they do it here too. So we found that component of the y velocity. Not a bad problem. Okay, so let's take a look at this problem here. A crate slides down a frictionless plane. We already did this. We did it with Charmander. The crate is constrained to accelerate parallel to the surface. Charmander, you can go back and watch the last video. Both the acceleration and velocity vectors are parallel to the surface. All right, so yep, we did all this before. All right, let's look at this problem here. Okay, so a ball rolls up the ramp and then it goes back down. Which is the correct acceleration graph? Okay. So just ask yourself one thing. They're asking you for the acceleration. What is the acceleration caused by? It's caused by gravity. Gravity doesn't change. If you are on the surface of the earth, okay, it really doesn't change. So you need to ask yourself, is rolling the ball up the hill going to change the acceleration due to gravity? No. No, it does not. Nothing can change that. No, it can't. Even when it stops for a moment. Right? You might say, but Dr. Wisby, it's not moving at the very tippy top of the ramp. It's not moving. Isn't his acceleration zero? No. Acceleration due to gravity is never zero. It's constant and it never changes. It's as constant as the North Star. I think supervillain said that in a movie once. I don't remember which supervillain it is, but it's always negative. It's constant. It doesn't change. There's only one. It's D. All right. Because even if this thing's going up the ramp, okay, velocity is changing, right? Velocity is decreasing. It's going down in a slope. And let's draw a picture. Okay, why not? We will draw all the velocities and oh no, I already shared my screen. Switch to the camera. Here we go. All right, so here's my let's see. We want to do, let's just do velocity up the ramp. Okay. And we're gonna do this as a function of time. Yeah. So we're gonna do position as a function of time. So this will be X over here. We're gonna do position, velocity, and we're gonna do everything. Okay. So, the position is going to look something like this. Okay, we're going to start off here, the really high velocity, then it's going to level out. Okay, and then it's going to come back down here. Okay, that's our position versus time. As this thing rolls up the hill, right, it goes up, it stops here for a moment at the very top. Right, our position's not changing for the briefest of moments. Okay, just that That infinitesimal amount of time that Newton was always talking about. He's talking about infinitesimal amounts. He's got an infinitesimal amount. Okay, so let's do our velocity here. Hey, we're gonna do velocity. Okay, so this is v in meters per second. Okay, and this is t here. Now, I love to draw graphs because I really feel like it helps me to understand it. Okay. So our velocity is changing. It's got a constant negative slope. It starts off positive and then it goes negative, and it goes negative right here when the particle stops. So this is going to look something like this. There's going to be a line here. Okay. So right here where the particle stops, our velocity is going to go to zero, and then it's going to become negative because now our particle is rolling back down the hill. Okay, I'll draw a little cartoon here. On this side, our ball is going up the hill there. And then on this side, hey, it's coming back down. Okay, little cartoons there. A little inset. Okay, and so over here, now the slope of my velocity is constant, and it's got a negative slope here. So that means if I draw my acceleration here, this is zero, and acceleration meters per second squared. My acceleration is always negative and it's constant because my velocity has a constant slope. And depending on the angle of the ramp, okay, so our acceleration, then we could find our acceleration. It's got a value of A equals G times sine of theta. So yeah, I threw in what we just learned. Sneaky. Yeah, making you learn and you didn't even know it. And we'll call this A of X because, yeah, positive is down. No, yeah, that's positive. We're gonna call that positive going down the ramp here. See, X positive. Okay, it's a constant value right here, and this is A of X. It is negative, actually. Should be negative because the slope is negative. All right, so negative A of X. We did that one. All right, let's go on here. Oh, skier. Maximum possible speed for a skier at Willamette Pass Ski Area in Oregon was the site of the 1993 U.S. National Speed Skiing Competition. The skiers started from rest and then accelerated down a stretch of the mountain with a reasonably constant slope, aiming for the highest possible speed at the end of this run. During this acceleration phase, the skiers traveled 360 meters while dropping a vertical distance of 170 meters. What is the fastest speed a skier could achieve at the end of this run? How fast could you get going? Okay, so it says, what do we know? That's the question here. What do we know? It doesn't matter if it was in 1993, but what we do know is the skiers traveled 360 meters while dropping a vertical distance 170 meters. What is the fastest speed at the end of the run? So what I'm struggling to understand here. Okay, so they traveled 360 meters down the slope of the mountain. I'm thinking, so that tells us that that's the hypotenuse. Okay. All right. So this one, we got to just make sure that we read the problem carefully. And Charmander is going to ski today. We're going to put some seeds on Charmander. He likes to ski, Charmander. Okay, so he's going down the hill. Whoosh. He's really cruising, man. Okay, Ash is after him, and he's trying to get away. He does not want to be caught. The Pokeball is. Where's the Pokeball? Oh, here's a Pokeball. Okay. The Pokeball's chasing him. They're kind of like drones, I would say, right? Ash Ketchum, he has these Pokeball drones. How do they always chase the Pokemon? I mean, You gotta have some kind of drone technology in those Pokeballs, you know what I'm saying? Okay, so we travel 360 degrees and Charmander descends 170 meters. That's how far he goes down. And he travels 160 meters and we'll use a red arrow for Charmander. He is using fire to make himself go faster. Obviously, he has flame jets that speed him up because he can breathe fire. And his tail's on fire, right? So, I mean, he must be able to like use that as a some kind of jet or something. Okay, what is the fastest possible speed the skier could achieve at the end of this run? Okay, so what do we got here? We don't have time. We don't know what the time was. Okay, so that's a big clue because there's only one equation without time, and we'll say that our initial velocity is zero. They started from rest. Our final velocity, that's the thing that we are after here. Okay, we don't know the time. We do know how far he traveled. So what equation should we use? Probably VF squared equals VI squared plus 2A times delta X. Well, we know what delta X is here. Delta X is 360 meters, but we need to get our acceleration. And so, do we need to know this value? Hmm, to be determined. They did give us this. During this acceleration phase, the skier traveled. Yeah, okay, so, but I'm still, is this, yeah, I think this is the vertical distance here. All right, what is it even asking? What is the fastest speed a skier could achieve at the end of this run? Okay, well, we're gonna solve for V of F. We need to get our acceleration. Ah, that's why, because we're gonna need to know what the angle of this thing was, right? We don't know the angle, okay? So we can't find our acceleration. All right, I'm gonna stop sharing the screen here. Yes, we don't know what the angle is. Okay, because the acceleration, remember, is going to be g times sine of theta. Where did we get that from? All right, let's draw it again here. Okay, we know that gravity is pulling down Charmander. Gravity pulls you down the hill. All right, but let's go through this one more time. We're going to make a line here perpendicular to the surface. Okay, and then we're going to have one that's going down. The slope is parallel to the slope here. And this is going to be AX equals G sine of theta. Okay, that's this side here. And this is the acceleration that we're after. We know that this angle, what did it tell us? Oh, we don't know that angle. That's what we're trying to figure out. But we do know that this angle here is the same as that angle there. So if we knew that angle, then we could just plug it in here. We're done. Okay, so that's why they gave us 170 meters here, because now we have the opposite side, 170 meters. We have the hypotenuse. Okay, so that tells us which equation should we use. Okay, the answer is it's going to be opposite over the hypotenuse equals sine of theta. Okay, I'll just write out here. Okay, so we're going to have, I'll call it y times r times sine of theta. We want to know what sine of theta is. We don't know what it is. Okay, so we're going to get it on the other side here. Okay, sine of theta on this side equals y divided by r, my hypotenuse. Okay, and then I'm going to take the arc sine of both sides. So I'll say arc sine minus 1. We're doing the same trig over and over. It's arc sine, arc tangent. Okay, and we got these triangles here. Okay, that's pretty much most of the trig that we're going to be doing. Sine arc tangent of, what's that? Yeah, I drew y over r. Okay, so arc sine of theta equals theta. Okay, so now I've got theta equals arc sine of y over r, and y here's 170. So 170 meters divided by my hypotenuse r, that's 360 meters. Okay, I drew the units in here because in a in a trig function, you can't end up with any units inside of here. It has to be an angle, so either radians or degrees, and it has to be unitless. So our meters cancel, and that's a good thing, right? We don't want any units in there. So we're getting our angle now, and I'm going to pop this into MATLAB. All right, so in MATLAB, then I'm going to have arcsine, so arcsine of D. So in MATLAB, the notation is A sine D, and then we put in our numbers as 170 divided by 360. Okay, that tells us, all right, our angle then is 28 degrees. So our angle is 28.2 degrees, 28 point. Well, actually, what I'm going to do is I'm going to leave these digits in here for now because I'm not done with my calculation. And I really don't want to throw those away until I'm done with my calculation because then you're gonna get more errors. All right, but I got a number here, and now I can find my final velocity. I got all the numbers. All right, so let's go over to this equation. Okay, so I got my numbers here. I'm going to use this color. Okay, so we have VF squared. I'm putting in the numbers over here now. And I know everything except VF squared, which is what I want to solve for. Okay, now we're not taking into account friction, but that's okay. There's very little friction. Maybe you just got your skis waxed, so the friction is small. It's not zero, but these guys start from rest, right? Your initial velocity is zero. Okay, so now I've got, I'm gonna have two right there. I'm gonna put in my acceleration, which is 2 times 9.81 times sine of my angle, and my angle is 28.1786 degrees. Right? And now I'm gonna take the square root of both sides. Okay, I'm not gonna I never put the numbers in until the very I should have found the square root first. Okay, oh no, I'm gonna take the square root of both sides here. There, I can just write it there. Okay, so now I get over here, I'm going to get VF. The square root of VF squared is VF. Okay. And then I'll have all this stuff in here. I'm going to plug this into MATLAB now. All right. So we are going to have the square root. So SQRT, that is square root times 9.81 times sine of D of 28.1786. I am putting in all the digits because I don't want to lose those yet. All right, I got my brackets there. Okay, so the final velocity is, that doesn't seem right. It's 3 meters per second. 3 meters per second. That seems a little slow. 3 meters per second. Okay, that is basically 6 miles per hour. Okay, we messed that. I feel like this is not right here. Okay, something is. We're talking about the Olympics. Okay, those guys are going closer to like over 100 miles an hour. Okay, so we messed up something. Let's look ahead here and see where did we go wrong. All right, I don't know what they're. Okay, what do they do here? All right, so x of f. No, we got our slope here, right? Hey, x of f is down. Okay, the slope length is 360 degrees. What did I do wrong? Did I not put a sine D in there, or did I mess up my angle? Okay, let's go here. I made a mistake. Okay, it happens. No, we got an angle of 28 degrees. Okay, we put that in. Okay, so my acceleration is g times sine of theta. That's what we did. Okay. And oh shoot. Ha. Oh, we forgot to multiply by delta x. Okay. Okay, there it is. We forgot to see there's a delta x right here. I knew it. I was like, 6 miles per hour. That doesn't seem right. See, I had a feeling when I saw that answer because I forgot to put in delta x. Oh, jeez. We need to multiply here by 360 meters. We forgot the delta x. All right, delta x equals 360 meters. Oh, that makes more sense. Okay, so I'm going to multiply by 360. Ah, 57 meters. Yeah, okay, this is more reasonable. Okay, 57 meters per second, or we're just going to say 58 meters per second. Okay, or if I double that, that's going to give me miles per hour. This is about 118 miles per hour. This seems much more reasonable for an Olympic skier, or obviously Charmander with these flames pushing him forward. Yeah, Charmander's going way over 100 miles per hour, and so are the Olympic skiers. All right, so we figured that out. That makes sense. Okay, let's continue on with this section. All right, we got the right answer. We had to get a little help there because oh yeah, 130 miles an hour. Oof, that's fast. Yeah, we had to get a little help there because I forgot to multiply that number in there. All right. All right, so section 3.4, we're going to be talking about 2D motion. And now we've talked about the X and Y. Well, we're going to talk about X and Y. Okay. If we have a projectile, then we have to treat X and Y separately. Okay. It is Charmander. All right. So Charmander is, let's say he is sliding down a hill because he loves to have fun. Okay, so here's Charmander. Okay, he's sliding down the hill. Okay, so how do we find the acceleration here? Let's say this is 30 degrees. Okay, we know that gravity is pulling Charmander down here. Okay. Um, but he's not going to fall straight down, right? He doesn't fall at 9.81 meters per second squared. If this is a slight incline, he's going to accelerate much slower than that. Okay, so we need to find that component of acceleration. And so what you do is you say, okay, the acceleration due to gravity is the hypotenuse of my triangle. And so what am I going to do? I'm going to make another triangle here. First, start by drawing the perpendicular line here. This is the base of my triangle. Okay, that's my base. And then here's my opposite side. Okay, so this is opposite and this is adjacent. And this is really important. This angle here is also 30 degrees. Okay, those are the same angle. Okay, and if you know that, because all the problems that you see, they're going to give you this angle here and they'll say, find the acceleration down the hill. Okay, all right, so that's not too bad then. Now we already saw the formula. Okay, so it's just a component of acceleration on this side. This is the opposite side. Remember, you can just take my triangle here. Oh, I've got a triangle. This is the opposite side here. I'm going to write that down over there. Okay. So this component right here, okay, right there, that part of my triangle is the opposites. Okay. And remember, I'm going to define positive x as going down this way. Right? That's positive x. Yes, it's going down and to the left, but you know what I can call positive x, whatever I want to. Okay? It really doesn't matter. I could have drawn my picture the other way, but I drew it this way. I'm saying that way is positive x. Okay? So, and my component here, I'm going to call AX. That's my X component because it's going to be parallel in this direction. Okay. And then the hypotenuse is going to be G. And so now I've got sine of theta there. Okay. That's my acceleration. So to find my acceleration, then it's going to be 9.81 times sine of 30 degrees. All right, let's plug that in. How fast is Charmander accelerating? Is he like, or is he more like, eh? Yeah, I think it's more like the second one. But let's just go to MATLAB and we will calculate it. All right. So now we said we have 9.81. I always throw the one in there. It's technically correct. You could just do 9.8. I mean, you could even do 10 if you wanted to. Okay, sine of 30. Right? It's 4.91. Now let's recall, maybe you don't recall, I don't know. But sine of 30 is it's 1/2 actually. Okay, so if you know that value, a long time ago, well, actually maybe not that long ago, but when you take math, you used to have to memorize these tables of different values. I, of course, never memorized it, but it's actually useful to know. So sine of 30 is 1/2. Sine of 45 is, okay, that's not so easy to remember. 0.7, I think that's actually 1 divided by the square root of 2. Yeah, it is. Okay. So those are just some useful identities. We've also got sine of 60. Okay, so that's what is that one? Okay, I don't remember what that one is, but it also had some convenient identity. Okay. So those are just some easy values to remember by. Okay, but we had sine of 30. Okay, so sine of 30 times 9.81. Okay, so 4.95. I'll write that down. So my acceleration in the x direction is going to be 4.9050 meters per second squared. Okay, so let's see. So that is Charmander's acceleration in the x direction, or we could just write x equals 4.9 meters per second squared. Okay, so what did we do? All right, we created a new axis system, and we said positive x is going down the hill. Thank you, Bulbasaur.